Hello everybody and welcome to the 7th logic lecture of Comp 0003. In today's lecture we're going to continue from where we left off in the previous lecture and discuss the semantics of first order logic. In the previous two lectures we discussed first of all the syntax of first order logic, so what does and does not count as a formula, and then I went on to describe how we can give a meaning to the function and predicate symbols that occur in first order formulas using something called a first order structure, where we pick a domain or a universe and then interpret the function and predicate symbols as real functions and real predicates inside that universe. So today the plan is to briefly recap that material, and then I think having picked some first order structure in which to interpret the formulas, I'm going to describe how it is that we should interpret a particular formula as being either true or false relative to that structure. So without any more messing around, I think let's go to the slides and I'll see you again at the end. So let us begin by recalling where we got to sort of by the end of the previous two lectures. First of all, the syntax of first order logic. Now remember that we have this concept of a first order language, which is given by a set of function symbols together with a set of predicate symbols. So for a first order language, I'm usually writing the symbol sigma, and that's given by curly f for the function symbols and curly p for the predicate symbols. Then we have the concept of a term. A term is either a single variable x, or it is a function symbol which comes with an arity k, the number of arguments that it takes, and it's a function symbol applied to k terms. So this is an inductive definition that explains how to build up larger terms from smaller ones. In particular, if f has arity 0, then it's a constant symbol, and this definition implies that any constant symbol is also a term just by itself. Next, we have the syntax of formulas. So the atomic formulas, also called predicate formulas, are given by a predicate symbol p in the language applied to appropriately many terms. So here I'm assuming that the predicate symbol p has arity k, and we apply the predicate symbol p to k terms, t1 up to tk. That's an atomic formula. Next we have all the familiar connectives from propositional logic, so negation, conjunction, disjunction, implication, by implication. And lastly, we have the two quantifiers for all x, a, and there exists x such that a. Now, these quantifiers come with a scope. So the scope of this quantifier for all x is said to be everything between these two brackets, so the formula a, and the same for the existential quantifier. At the same time, this gives rise to the idea of bound and free occurrences of variables. So if we have a variable x occurring in a formula, it is said to be a bound occurrence if it falls within the scope of some quantifier with the same name, so either for all x or exists x, and so in other words, any x occurring in this a, for example, is bound by this quantifier for all x. If an occurrence of a variable is not bound by any quantifier, then it is said to occur free in the formula. And remember as well, I didn't put it on the slide, but remember that we call a sentence a formula with no free variables. So that's the syntax of first order logic on one slide. And next on this slide, I'll just recap the idea of a first order structure which interprets a first order language. So given some first order language sigma, which is functions f and predicates p, a first order structure for that language is one of these guys, M, which consists of D, which is a domain or universe in which we interpret everything, FM, which is the collection of interpretations of the function symbols, and PM, which is the collection of interpretations of the predicate symbols. Now, just to make that a bit more precise, D has to be a non-empty set of objects, and it's called the domain of that structure. So it could be a set of numbers, or a set of people, or objects of any kind. Next, for every function symbol in this curly f, there is a real function, little f with a m superscript, in this guy here. And that is a real function of the appropriate type on the domain. Now, when I say of the appropriate type, I mean that if the function symbol has arity k, then fm should be also a function on D of arity k. So, in other words, that's just really saying that that we respect the arities when we interpret functions. Otherwise, we're free to choose what the function is. And similarly, PM is the collection of interpretations of the predicate symbols in the set curly P. And so remember that the interpretations of predicate symbols are predicates or relations. So, for example, a binary predicate symbol in the first order language should get interpreted as a binary relation on the domain. So, not to over-egg the point, but I wanted to return to this Humpty Dumpty theory of language, which I mentioned in the previous lecture. Remember that Humpty Dumpty in Through the Looking Glass says, when I use a word, it means just what I choose it to mean, neither more nor less. Now, this is really just to make the point again that the function symbols and predicate symbols in a given first order language are just that. They are just symbols written down on a piece of paper. And even though you might think those symbols have a normal meaning, when in fact we're free to give them whatever meaning that we choose, as long as we respect the arity of the symbols. So when we specify a first order structure for the language, then we're choosing both the universe that we're talking about and the meaning of all the function and predicate symbols. By the way, I don't know why Humpty Dumpty is commonly depicted as an egg. In the nursery rhyme in which he appears, it's never said that he's an egg. He is supposed to fall off a wall and be sort of unable to be put back together again. So from that point of view, it does make sense that he's a big egg. But I just suppose looking at it now, it's a bit of it is also kind of a mystery how that happened. I imagine he was probably supposed to be a soldier or something like that in the original nursery rhyme. Anyway, sorry, I'm getting distracted. Let's move on and go over the objectives for today's lecture. So I'm going to suppose that we have chosen already a first order language. So we've specified our function and predicate symbols. And I've also going to suppose that we've chosen a suitable first order structure for that language, which I'll call M. And suppose that the domain of that structure is D. So we've chosen a meaning for all the function and predicate symbols in the language. Now, can we say whether an atomic formula or a predicate formula with P applied to some terms, T1 up to TK, is true or false relative to that choice of structure? Well, actually it still depends, because we still have to interpret the variables. There may be sort of, remember that we can, that any variables are terms, so X, Y, Z, and so on. And you can imagine that these correspond somehow to objects in a domain, but they're not fixed objects. They're variables, and so they vary. So this gives rise to the idea of a valuation. So the idea is that even when you've picked a fixed meaning for the function and predicate symbols, the variables denote elements of the domain or objects in the chosen universe, and they can vary, but we can talk about any particular valuation or any particular chosen interpretation of the variable, and for that we use something called a valuation. So having picked a valuation, we can then give every first order logic formula a truth value. So relative to a particular language, a particular structure, and a particular valuation, we can read any first order logic formula in that language as being either true or false. And so we're going to go on and do that now. So suppose that we have chosen some first order structure M, with domain D and functions fm and predicates pm. Then a valuation for that particular structure is a function that sends variables to elements of the domain D. So I'm going to usually write the Greek letter rho to represent valuations, and I'm writing vars here for the set of all variables, so our little x, y, and z, and so on. So a valuation, rho, is a function that maps the variables to elements of the chosen first-order structure. Now, it's convenient, technically, to have valuations sending terms to elements of D and not just variables. So given that we've already chosen the first-order structure, we can extend valuations to interpret terms by the following definition. We already have, remember that a term is either a variable or a function symbol applied to appropriately many terms. So we already know what a valuation does to variables, and then supposing that we have a function symbol applied to some terms, then we just say that the valuation of that term, the function applied to some other terms, is just the interpretation of the function symbol applied to the interpretations of all the terms. So that's a recursive definition, and you can see that the effect of it is that if I apply a valuation to a term, then what happens is that all the variables get interpreted according to the valuation, and all the function symbols get interpreted as the functions in the first order structure. So let's go on and see an example of this using the first order structure for piano arithmetic that we saw in the last lecture. So this first order structure has domain n for the natural numbers, and for each of these symbols, well, we have 0m is 0 in the natural numbers, sm is the successive function, plus m is addition, and so on. So in this structure, all the symbols of piano arithmetic have their normal interpretations. So I'm going to let rho be a valuation for this structure, so it's going to map variables to the domain of the structure, which in this case is natural numbers. So, of course, there might be infinitely many variables, but I'm going to just choose one. I don't care about the other variables. We're going to say that rho of x is 5, rho of y is 8, and rho of z is equal to 3. Now then, so here's a term in the language, x times s of sy plus z. Now, so that is basically x multiplied by the successor of y plus z. So if I want to interpret that term in my evaluation, well, in fact, the answer should not surprise you. All of these function symbols will get interpreted in the expected way, and we will end up replacing x by 5, y by 8, and z by 3. So if I apply rho to this term, then that is equal to rho of x times, and this is times m because it's the real function, successor of m applied to rho of y plus m rho of z. Now you can see, if you can kind of work through the clauses of this previous definition, this one here, one at a time, and see that that is kind of correct. You'll have to apply it recursively a few times, but that is where you'll get to. So we have this, as I said, all the variables get interpreted according to the valuation, and all the functions get interpreted according to their interpretation in the first order structure. And so just by a simple replacement, that is 5 times successor of the successor of 8 plus 3. And then you can see, well, okay, the successor of 8 is 9, plus 3 is 12. Take the successor of that is 13, so that's 5 by 13, which is 65. So if I just take the valuation of these of these variables, then everything works out in the expected way. And so, although it's taken us quite a while to get here, we are now finally in a position to define the truth value, true or false, of a first order logic formula relative to a given interpretation. So suppose that we've fixed a first order language, sigma, a suitable first order structure, M, for that language. So we have a domain for the structure and we have an interpretation of the function predicate symbols, and we have a valuation that interprets every variable as an element of the domain of that chosen structure. Then I'm going to write this notation, M models row A, to mean that the formula A is satisfied or becomes true relative to the choice of structure M and the valuation row. So the row is a subscript on the satisfaction relation here. That's just a sort of standard convention. So in the case where A is an atomic formula or predicate formula, P applied to some terms, we say that P of T1 up to Tk is true relative to the choice of M and row if the interpretations of the terms, which is row of T1 up to row of Tk, belongs to Pm, which remember is a carry relation on the domain of the structure M. So let's see a concrete example of this. So let's think about our structure for piano arithmetic, where everything has its standard arithmetical interpretation. And let's think of the atomic formula x equals y times z. Now that's an atomic formula. This is a predicate symbol. I've written it infix, and it's applied to two terms, x, the variable, and y times z, which is a term built from the function symbol times and two variables, y and z. So by this definition, that is the case if the interpretation of the two terms, row of x and row of y times z, belong to the interpretation of the predicate equals, which is a binary relation on natural numbers. And remembering that our definition of valuations extended to terms just says interpret the functions according to the structure. So that is the case if row of x and row of y times row of z are in the interpretation of the equality relation. And that is going to be the case if and only if, since we're interpreting the equal symbol as meaning equality and the times symbol as meaning multiplication, that will be the case if and only if row of x is actually equal to row of y times row of z. Now, before I go on and show the satisfaction relation for other formulas, in order to interpret quantifiers, we're going to need just one extra piece of machinery. So I'm going to require the concept of updating a valuation. So suppose that I've got a valuation row that sends variables to elements of D. Now I'm going to say, consider the valuation which is exactly like row, except that I specifically want it to send x to the element little d. So suppose that I have a variable x and an element small d in the domain. Then the updated valuation, row with x maps to d, is defined by, well, if you apply row, the updated valuation row x maps to d to a variable y, then if you apply it to x, then it must send it to d. So the whole point is that this valuation is exactly like row, except that it sends x to d. So if you apply it to a variable, which is equal to x, then the result is d, and otherwise it just returns exactly what the original valuation would have done to the variable anyway. So this is just a mathematical way of saying row with x maps to d is the valuation which is exactly like row, except that it sends the variable x to the element d, which is exactly what we say here. And we're going to need this to interpret quantifiers. And we'll go on to show the satisfaction relation for all formulas of first order logic on the next slide. Okay, so now I can go on to give the definition of the relation M models row A, or M and row make the formula A true. So I'll give it by induction on A, induction on the structure of A. So in the case where A is an atomic formula, we already saw that that in that case, if A is a predicate symbol P applied to terms T1 to Tk, that is made true in M and rho if and only if the interpretations of the terms belong to the interpretation of the predicate symbol. So we saw that before. Next, we have the clauses for all the propositional connectives, negation and so on. So these just mirror the exact same clauses as in the propositional logic case. So for in particular, M and rho make not A true, if and only if they do not make A true. And then here I've just kind of, blanket put down the clauses for all the other connectives, which again are exactly the same as in propositional logic. So for example, in particular, we have that M and rho make A and B true if M and rho make A true and they also make B true. Similarly, we have this clause for A implies B, remembering that A implies B is equivalent to not A or B. So M and rho satisfy A implies B if and only if they either do not satisfy A or they do satisfy B. So that just leaves us with the quantifiers, and this is why we're going to require this notion of the valuation update that we saw on the previous slide. Now consider a formula for all x A. Now think about what that formula really means. It's kind of saying for all possible valuations or all possible values or interpretations of the variable x, the formula A becomes true. In other words, A is a true statement no matter how you interpret the variable x. So the clause, the satisfaction clause, sort of mirrors this by saying for all x A is satisfied by M and rho if for all possible interpretations of x, so for all small d in the domain, if I update the valuation to interpret x as being that little d, then the formula A still becomes true. So in other words, M and rho, but interpreting x as little d, satisfy A, and that has to be true for all possible small d in the domain. Similarly, M and rho satisfy exists x A if there is at least some way of interpreting the variable x that makes the formula A true. So for some element in the domain, if I interpret x as being that element, rho with x maps to d, then the formula A is made true by M and rho, but interpreting x as that d. Let's see how this plays out in a concrete example. So I'll take the same structure as before, so with domain natural numbers. So this is my structure for piano arithmetic. I've been a bit lazy and haven't written it down. And this row, that's a LaTeX error there. I will correct that for the online version. But so row, but this row is a valuation for the structure. Now let's consider the formula exists x such that 0 is less than x. So there is, informally that formula should mean there's a number that is larger than 0, which is obviously true. And if we just work through the clauses of the satisfaction relation one at a time, we can check that that actually is the case. So by applying the clause for existential quantification on the previous slide, M and rho satisfy exists x such that 0 is less than x, if and only if M and rho with x updated to n satisfy the body of the formula 0 is less than x for some element in the domain. So in other words, for some natural number n. Now this here, 0 less than x, is an atomic formula. It's a predicate symbol, less than, applied to two terms, 0, which is a constant symbol, and x, which is a variable. So by the clause for atomic formulas, I have to take the valuation, which is this whole thing, rho with x maps to n, and apply it to both terms. So I have to interpret both terms 0 and x according to this valuation, and I have to check that that is a member of the interpretation of the predicate symbol. So it has to belong to the relation less than in the structure M. Again, for some natural number n. So I can simplify this a bit, because rho with x maps to n of 0 is just 0m. I mean, it doesn't, there's no variables in this at all, so we just interpret 0 in this valuation as just the interpretation of that, of the symbol 0 in the structure, which is 0m. And if I apply rho with x maps to n to the variable x, well, I mean, by definition, if I apply this valuation to x, I should definitely get back n. So this really means that 0m and n have to belong to less than in the, for some natural number n. And although, so I'm kind of going into mathematics here, but since in this structure we're interpreting the less than symbol as meaning less than, and the 0 symbol as just the number 0, well, then in this structure, what it means is simply that 0 has to be less than some natural number n, which is a true statement. Of course, it might not have been true if I had interpreted the less than symbol in a different way, but otherwise it would be true. So yeah, okay, so I think that's about it. Let's go on to review satisfaction and validity in first order logic as opposed to propositional logic. Before, we had the idea of a formula being satisfiable, which means there's at least some way of making it true, and of being valid, which means that it is always true. Now, that sort of carries over to first order logic, but now we have more moving parts. We have valuations and we have first order structures, and so there's different ways of choosing all of those. And so we have sort of two concepts really of satisfiability and two of validity. So the formula A is said to be valid in the first order structure M, which I write as just M models A. Again, look, there's no valuation in the subscript here, and that's because it means that M and rho satisfy A for all possible valuations. So this means, supposing that I've chosen the meaning of the functions and the predicates, then no matter how I interpret the variables, the formula always comes out as being true. We can even go further and say that, well, a formula is just valid, not valid in a particular structure, but just generally valid, if it is valid also in every possible first order structure for the language. So no matter how I interpret the function and predicate symbols, and no matter how I interpret the variables, the formula is valid. So it's valid in a structure if it's valid for all possible valuations for the structure, and it's valid if it's valid in all structures. And the same is true for satisfiability. A formula becomes satisfiable in the structure M if there's at least some way of making it true. In other words, there's at least one valuation rho such that M and rho satisfy A. And the formula A is said to be just satisfiable if there's just some structure in which it becomes true. So it's satisfiable if there's at least some way of interpreting the functions and predicates and some way of interpreting the variables such that the formula comes out true relative to that chosen interpretation. By the way, and you should be able to prove this kind of straight away, that if a formula is valid, then it is valid in any particular structure you might choose for it. So if it's valid, then it's valid in M, where M is any chosen structure. And that means if it's valid in M, it's also satisfiable in M. And if it's satisfiable in M, then it's also just satisfiable. More or less immediately by definition. So just to return to our example, so we saw that this formula is true, and actually I didn't have to assume anything at all about the valuation rho for this formula to be satisfied by M and rho. And that shouldn't surprise you because this formula has no free variables. So in some sense, of course, it doesn't matter how we interpret the variables. But yeah, so we saw that for any row, but for our particular interpretation of less than and 0, the formula exists x such that 0 less than x becomes true. Therefore, this is an example of a formula that is valid in that structure. It's valid no matter how we interpret the variables. In other words, it's made true in every valuation for that structure, and therefore it's valid in that structure. However, it's not valid, it's full stop, because it is quite easy to find structures, in particular interpretations of the less than symbol. For example, just take the interpretation of less than symbol to mean more than, for example, then you can see that the formula is no longer true. And for that reason, it's not generally valid. And that brings us to the end of today's lecture. Hooray! I think the next lecture will be mostly an exercise in consolidation. So we'll get some more practice with the semantics of first order logic. And I'll talk about some cool and hopefully interesting equivalences that hold in first order logic and how to make use of those. And well, so I think that's about it. So I shall look forward to that, and I hope you do too. Until next time, take care.